Good day, everybody, and welcome to the OptiSystem webinar on Matlab and C++ integration. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Damien Merrick. Before we begin, I'd like to review the layout of today's webinar. So during the presentation, we're going to launch 3 polls, such as the one you're looking at now. Each poll provides Damien with helpful feedback for guiding the presentation, so your participation is greatly appreciated. We're also going to handle questions at any time during the presentation, but we're going to be using the questions section only. You'll find the questions section in your GoToWebinar control panel. Please note that since we have a packed house today, we're not going to be handling questions via the raised hand option. So we ask that you please type all questions into the questions section only. And in the case where you'd like to keep your question completely private, please send it to support@optiwave.com and we'll respond to you via email. If for some reason we're unable to answer any questions during the webinar, we're going to jot down the question and reply to you afterwards. Also in the GoToWebinar control panel, you'll notice that we have 2 handouts available. Please feel free to download these at any time. And lastly, we'll be recording the webinar and distributing it to all registrants via a download link that you'll receive in an email tomorrow at the exact same time, so 10 a.m. Eastern Standard Time. In order to access the recording, you're going to need to use the same name and email that you used when registering for the webinar. So if there are no questions at this time, I'd like to introduce your presenter, Senior Photonics Application Engineer, Damien Merrick.
Hello, thanks for the introduction. Yeah, so today we're going to be talking about co-simulation with Matlab and C++. And I'll let the poll kind of work its way out a bit here while I share my screen. Make sure everything's good. All right, so now you should be able to follow along with the webinar. So my name is Damien Merrick, and I'll be presenting a slightly different webinar than the previous ones, more about the use of our software in conjunction with other software, kind of an interface webinar. And we'll be presenting the Matlab component and the C++ component. The first half will be dealing with the C++ and the second with, the first half with the Matlab and the second with the C++. Right, so the topics will be a quick walkthrough of the Matlab component and using Matlab with OptiSystem. We'll be passing data from OptiSystem to the Matlab component, and I'll show a very simple binary switch that also uses a low-pass filter. Continuing on, I'll show some default or samples that come with the OptiSystem software, which is using Matlab to plot kind of the optical spectrum. So it's like acting as an optical spectrum analyzer. And if we have the time, I'll show one more example where we use Matlab to actually start and call OptiSystem. So in this case, you're not actually using a Matlab component, you're actually controlling OptiSystem from sort of the scripting engine of Matlab. You can control OptiSystem and run simulations via Matlab. In the second half, I will again pretty much show the same thing but in C++. This is because C++ is a little more involved, a little more complex, and I want to make sure that there's nothing really new. Just the only thing that's new is going to be that it's in C++. So again, I will show passing of data, how to get data in and out of the C++ component. The same example of using the binary switch. And then finally, one interesting example where we use NuPlot, which is open, I think it's open source. Anyways, it's a free to download library where you can plot fields and things using it. And we have hooked into that via our C++ component. So it makes it really easy to have kind of plots that you can use to debug your C++ component. All right, other things we'll discuss is some debugging techniques and passing parameters to both of these components. We've also got that down here. So what is the Matlab component? As you know, OptiSystem has a big and large library of components, and we have a lot of them, and most of them that you'll probably need are there. However, some engineers have a specific component they need. Maybe it does a very specific operation. So this allows the user to design and model their own component and create their own model using the Matlab language. This also gives you access to MATLAB's very large library of numerical routines, right? They have matrix, obviously matrix routines to do inverses and solving matrix equations. They also have a lot of FFT and signal processing libraries, so those are all available for you to use because it's in the MATLAB application or framework. The interface with MATLAB is relatively simple, actually, and I'll show you how simple it can be in the live demo here. The only requirement is that, of course, you have to have OptiSystem installed, and also you must have MATLAB installed. And if you want to, if you have created your MATLAB component, which is usually going to be inside a MATLAB M file, if you want to share that with someone else, they will also have to have MATLAB installed. So it's a little less portable than the C++ component. It's also a little bit slower. Not so much that the MATLAB language is slow, although it can be considered a bit slower than a C++ compiled language. It's more that the MATLAB COM application has to be started during the simulation, so that actually can take a couple of seconds depending on your computer. So it's a bit slower than native components, so if you're doing really in-depth simulations, that'll be a bit longer. The other thing I can do is you can run OptiSystem from MATLAB. So that's one of the pros of MATLAB. You can use it to control the OptiSystem framework simulation. In contrast, the C++ component, a little bit different, although again, it's also fairly similar. You can create any type of component you desire. Programming in this source file I'll show you. You can write any code in, include any classes, include any other libraries. We also give you access to our numerical routines. Not all of them, but we give you lots of ones you might need. For example, you can take an optical signal, transform it into the frequency domain using our FFT routines. We have some mode solvers for fibers, including in there as well. And the best thing is you can use any other C++ library. There's lots of libraries out there that are used to do anything. So you could probably find one that does signal processing and use that, or any other. There's lots of C++ libraries. So I don't even know where to start. The interface is a little more complicated. You have to be able to be a little comfortable with C++, but it's not too bad. We've really set it up to make it as easy as possible for users. You'll need Visual Studio 2013 Community to compile the DLL of the component. I'll show you how that works in a bit, but you'll need to download 2013. It's free, so that's not a big problem, but you'll have to download it. However, when you share your DLL, if you feel like you want to share it with someone else, you don't need to have Visual Studio, obviously. It's a DLL, so you could just send the DLL in an email, and they can put it in their folder, link to it, and then their component will work exactly like yours that you have made on your computer. The other big positive aspect to the C++ component is that it's pretty much the same speed as native components, right? You're compiling it into machine code, into a DLL, and the linking is a lot faster. You don't have to start any other software framework to get it working, so it's pretty much as fast as any of our native components. So that's one of the big pluses as well. And then I think that's the end of the PowerPoint presentation. We're going to get into the live demo now. If I can change my screens here. Yeah. All right. So again, we're going to be starting with the MATLAB component. I have OptiSystem started over here. I'm going to create a new project, new layout here. So we've got a blank layout. First thing I'm going to show is how to pass data into the MATLAB component and pass it out again. So the component's not going to do anything. It's just going to act as kind of a transparent component, really. But it'll illuminate some of the things down the road. So first we're going to need a bit sequence. So we're going to use a random bit sequence here. Just throw it down right there. And then we're also going to need the MATLAB component, which can be found in the folder External Software Tools, MATLAB Library, MATLAB components right here. And that's pretty much it. The first thing I'm going to do is I'm going to change the default signals on this MATLAB component because we're using a binary input. So if we go into the properties of the Matlab component by double-clicking, we can go to the Inputs tab. This controls what types of inputs are going to be coming into the the Matlab component, and then later we'll change the outputs. So we're going to have one input, but it's not going to be optical. It's going to be binary, right? Ones and zeros. And the output's going to be the same. We're going to just have a binary output. So here I switch the input and output to binary. And I'll explain a little bit about the main parameters here. So in the run command, this is the first command that Matlab will run when it's called through this simulation. When you start simulation, it runs all the components up till you get to the Matlab component, and then it'll start Matlab and it will call whatever is in this command. So right now we just have it set to the output port is going to be equal to the input port. So this is just copying the input to the output and all the data structures that are necessary. So this is one of the most important options here, because you change this. Later we'll change this to call a Matlab function or a Matlab script, which will be inside an M file. And I'll show you how that works, but first we'll just start with this. And also this load Matlab checkbox. If I don't click this right now, if I run the simulation, it will first run the simulation, and then when it gets to the Matlab component, it will then open up Matlab and then execute the command and then close Matlab and then finish simulation. If I load Matlab and hit OK here, it'll kind of pre-open Matlab. You'll see down here it's opened up the command window. So now it's already open. If I connect these components here, I'll put some visualizers down just so we can be sure we're getting everything proper here. So I have a binary sequence and another one output here. If I run the simulation, it won't need to open up the Matlab command window because it's already open. So it'll be pretty quick. I can just run it. It's already done. In the input, we have this random bit sequence. And the output, we have the same exact random bit sequence. Now that we have the command window open, we can investigate kind of what these data structures look like. What's OptiSystem actually passing to Matlab? In Matlab, to do this, to see which variables are kind of in the workspace, you just write workspace. Since we loaded Matlab before we ran the simulation, it'll stay open, so we can do this. So you see in the input port, it's a data structure. We can double-click it and just kind of navigate throughout the what it contains. So here we see it has a string. This is the binary. It has the bit rate of the sequence and also the actual sequence of zeros and ones, right? So these are just zeros and ones. And the output is going to be exactly the same as that. I'm not going to look into it because you can use your imagination to see what it's going to look like, but it's going to be exactly the same. So how would we edit things in Matlab? Say we want to make a component. Well, you're going to want to create an M file. So I'm going to exit out of this, and I'm going to, maybe I'll start Matlab here. I'm going to create an M file, and then I'll use that M file and sort of link to it from the Matlab component. So we're going to make a new script, and it's over here. I'm going to quickly just save it on the desktop as, I'm going to make it take the binary not of the signal. So I'm going to call it not, with all capitals, and we'll save it. So now on our desktop we have this not.m. It's basically a text file. Whoops. You can see down here it's there. And I'll just quickly write what we usually do. We say output port 1 is equal to input port 1. This will copy the input to the output. So all the structure will be the same. The data structure will be exactly the same. I'm going to save this. Before I go any further, I'll just make sure that I can link to this file correctly. So it's been saved. It's not doing anything interesting. It's doing the exact same thing as we already had. And now if I go into the Matlab component, instead of running this command, I can change it to run my new M file, which I've written. So I'm going to say run not, right? So this is, it'll look for, the Matlab engine will look for this script file called not and try and run it. And it'll use the default search path, which includes the Matlab default search path, as well as whatever folder the OptiSystem project is in. So I have not here. I'll save this. I'm going to save my project file into the desktop so that it's in the same directory as the code I just wrote. I'll just call it project 1. So now it should be able to find not, and right here it's going to be running not. So if I run it, if I get no errors, you see here I didn't run the Matlab beforehand, so it takes a little longer for it to open up. But at the end, the result is the same. We have the same output. That's good. And now I will do a simple operation just to show you how to modify the things inside these data structures. So let's take the not. So output port 1. The structure that contains the binary sequence is called sequence, if I remember correctly. And we'll set this equal to the input port 1 dot sequence, this is not just a single variable. This is a whole like vector or a whole single column of binary values. We will add 1 to it, and we'll take the mod. Here, let me see if I can do this properly. Mod is a built-in Matlab function which finds the remainder with 2. Well, the second argument. So I'll take the mod of the input sequence, add 1 to it, and then divide by 2 and find the remainder. That will actually do the same thing as a not logic. If I've done this correctly, it should work. I'm going to load Matlab beforehand, before I run not. And then I'm going to run it. All right. So if it all worked properly, we should see the output is sort of the opposite of the input. And I did it correctly. As you can see, look at the input here. The input starts at 0, whereas now the output starts at 1, and then they're the opposite of each other. So that's how you do a very simple operation with a Matlab component. And I'll just show you kind of the shapes using the workspace. I'll just show some of what the other other signals look like. So let's change what the inputs are. We'll have now. Let's just do an optical signal as well. So we'll add an optical signal. This input 2 will be optical, as I just said. The binary, we'll just keep it as the output. And sure, we'll just run not. It's not really important. We just want to look at what it looks like, the optical signal. Okay, so now our second port here of the Matlab component is going to be optical. So let's find an optical sequence. In the transmitters library, we will choose an optical transmitter right here. So this basically is just a default component in a OptiSystem where it just basically generates an optical NRZ signal. So it's done everything for us. Now in the Matlab component, we'll load Matlab again before we run it, so that's already open and doesn't close itself. And we will run the project as it is. And then, as we did before, we can write workspace in here, which will open up the variables. We have this new input port 2 here, which is our optical signal. And we'll see that it's a little bit different, but not too different. So first thing's different is we have an optical label string as the type. The channels corresponds to the center frequency or the carrier frequency. So here it's 193 terahertz, or 193.1 terahertz rather, which is about 1.55 microns telecom wavelength. And it contains some other structures. Here we have the sample data, which has again, the central frequency here, the time, and the signal. So the time is it's the time in I think this is femto, no, sorry, this is in not femtoseconds, but nanoseconds. And the signal, which is a complex value for one of the polarizations. If you have more polarizations, there will be more sampled signals. If you have more channels, because you have more than one channel, because you have more than one central frequency, you also have more of these sampled signals. And if you have noise bins, which are like kind of average noise values, those will be included here. If you have parameterized signals, there's lots of signals that these optical signals can hold, and they're the most complex signals that we have. Another thing that they can hold is the spatial information. So if you have a mode, if you have this input connected to an optical fiber that has a modal distribution, you'll also get the spatial kind of grid. So the field as a function of the x and y coordinates for each mode. So this can get pretty large, this input port 2 for optical signals. The electrical signal I haven't shown, but it's very similar to both this and the binary. It's like the binary in that I believe only has one channel, and it has sampled, but it's sampled has a double value instead of a binary. So that's how you would look at the sampled signals. We also, one of the handouts that we have is actually it's actually kind of a document that shows what kind of data structures are in each type of signal. However, I personally always forget, and I just start Matlab, look at the workspace, and then I just code from there. That's how I do it. We can also pass parameters to the Matlab component. For example, I go into the Matlab component here. If I add a parameter, I can give it a name. I'll call it temp, which stands for temperature. And minimum value, we can say, we'll keep it at 0 for whatever reason. And I'll give it a value of 5 just to start. This is just an example of how you would pass a parameter. So we have this parameter now, which is called temp, has a value of 5. So someone could control the Matlab functionality. Like you could make, if you're modeling a fiber, you could say this is the fiber length. This will affect your Matlab code. Or you could, type of gain or something like that. Just any parameter you want to pass to your Matlab file. If I load Matlab again, I'll just show you how this comes into the workspace. I can run it. And then as we do, we just write workspace in here, which is a Matlab command. We see all our variables that are stored, and we have this temp variable. So now you can, in your script, in your not script, for example, you could write code that depends on this temp variable as if it was there, and it will be there. So that's useful. You can also, for debugging Matlab, if you don't want to have to run OptiSystem every time, you're looking at your code in Matlab and you have some bug in it and you don't know what the problem is, what you can do is open up the variables. Sorry, I want to open up all of them. I think I can do that. Oh, I did it before. Here. You open up all your variables. There's also a command you can use, which is just save. And then you just simply save it as this .mat file. You can put it on your desktop. And then if you're in Matlab, let me run Matlab again. If you're running from the kind of the Matlab interface, you can then just load this mat file, which is on the desktop. And oh, I didn't save all of the variables, but there is a way to save all the variables. There's a command you can use. And you can then run you gotta run not, right? You could run not from here. I don't have the input ports because I forgot to save them, but you can see how you could use the workspace and .mat files to kind of debug your code. That's how I would do it, at least. Yes, so I've discussed how to pass a parameter, and now I can show just some quick examples of different things we have. We have a quick question here. How does the mallet component handle noise? So, like I was saying, we have those noise bins. I can quickly show if I can get it working here. I think in the transmitter we can add some noise. Let me see. I think this will add some noise bins. I don't know if it's going to be converted. Convert noise bins is set to it'll convert right now. I'll quickly try this. When you have convert noise bins, basically it converts the noise bins to sample signals, so it won't show up. But if I do this correctly, I've just said don't convert it, it should show me the noise bins. The noise bins are basically, it's an easy way to handle large bandwidths, right? Because if you have a large bandwidth, the sample signals become very large. But if you model it as a range of frequency that has an average power, like a noise bin, you have a bin of frequencies that has the same power, then you can save a lot of memory. So it's just kind of a trick that we use in OptiSystem. But hopefully this works. Let me just try it. Going off script here, so I could run into some bugs. Input port 2, which is the optical signal. It should show up, right? Yeah, so it should show up here in the noise. It's just separate from the sample signal. And you'll see here that you have a power, so there's not many noise bins here. In fact, I only have one range of frequencies, which is considered noise. So we have a lower frequency and an upper frequency, and then kind of the average power of the noise in the X polarization and the Y polarization. And if I look in the Matlab, if I had put in a visualizer down here, you'd see the noise. And if I put it here, I run it again. Right, so this is the noise bin. It's just a block. Very simple model. You just have a range of frequencies that has the average power, and it's modeling average noise. OptiSystem has a way to convert this really quickly into sampled signals when you actually need the noisy signal. So that's how you would do the noise signal. It's just a different signal, but it's still included in that optical signal that we pass in Matlab. Now I'm going to quickly show some just a quick example. This took a little longer. Not that it's bad, but I don't want to bore you guys too much. The best way to understand these is just to do it yourself, really. It's just to get in here, do some simple examples. You could watch me all day, but if you don't just go and try it, you're going to be having a hard time. So we have this example here called the binary switch right here. All it does is you give it a binary sequence, and it modulates this continuous wave laser, and then gives you an output. And you'll see here, it calls this command binary switch, which if I go into this directory where I have this project, right here I have the binary switch, and this binary switch M file actually calls this low-pass filter function. So I can open it with MATLAB. Right, so you're in MATLAB now, so you can call any other function. You can create MATLAB files that are functions, and you can call them from your script that the OptiSystem is going to be calling. So here, low-pass filter, right? It just uses the MATLAB FFT, does a shift, and then applies a very simple filter. And you can look at this later, but basically you give it a signal and frequency and a time constant, which is kind of the pole of the filter, and it returns the filtered signal. And now if I open up quickly to show the binary switch, this is a very simple model of a binary switch. I use the time constant just to model a finite rise time, right? So usually a switch, it takes time for it to go from 0 to the max value. So I just use a low-pass filter to just kind of filter out the high frequency stuff so that you get a slower response. So here again, we have our very common, you copy the inputs to the outputs. I have two optical outputs, the one switch that's at the top port and one switch is the bottom port. And they're both optical signals, so I'm copying the input port here. And then I have some just error stuff, so if you make an error, it'll tell you. And then down here, it does a multiplication of the input with the binary sequence. So right, if the switch is 1, that means that the top output will be not changed. But if the binary signal is 0, then the output will be 0, like a switch. You're turning it on and off. The other port is the opposite because it's switching between the ports. So you'll get the opposite. It'll be 1 when the binary signal is 0, and it'll be 0 when the binary signal is 1. And then down here, I'm just applying the filter to all the signals. You'll see here I have this amount of sample signals because there might be more than one sample signal. There might be 5 channels, and so this makes sure I loop through all of them and apply it to every single one. I'll just quickly run this to show you how it functions. We have YouTube videos on this as well. There we go. So we have the optical signal, right? It's being switched on and off. The input signal is a constant 1 milliwatt, and the output top port is going to be switched, and then the bottom port will be, the bottom port will be the complement. So you see it's when this one's high, this one's low, and they both have a finite rise time and fall time from the low-pass filter. So yes, this is how you would do a very simple binary switch in Matlab. Again, if you want to see the code and try it out for yourself, we can send you links to that, and they're on our website as well with a YouTube video. You can go more in detail with that if you'd like. And I'll show one more example, but then I'll have to move on to the C++ component. Right here, we're using the Matlab component to plot the frequency. So it uses the DFT or the FFT in Matlab, and then plotting that in Matlab. To make sure your plots stay plotted and don't disappear at the end of the OptiSystem simulation, I got to load Matlab first before running the simulation, which I'm going to do like I did right now. Now if I run it, it'll happen exactly as you expect. So here we have the frequency and the power, and we can compare that to our own OSA plot, and they're very similar. Might be some differences if the FFT is slightly different, the Fourier transform, but otherwise they'll be very similar. And you can use this to plot anything in OptiSystem, in Matlab, right? So you can use any of the plotting tools you'd like in Matlab. This is just a simple example again. So I have one question here. Oh, sorry, it's kind of a private question. Just asking about the low-pass filter file. I can send that file out to you. It's also included, I think it's on the website. If it isn't, it probably should be, or I should make sure it's up there. I don't want to guarantee that it's a very good low-pass filter, but you can use it if you'd like. There probably is other better ways of doing a low-pass filter. I did a really quick way of doing it. So we're going to be switching now from Matlab to the C++ component. So we'll just fire off another poll here, get that going while I take a drink of water. We're getting into the more advanced programming stuff here. C++. I'm just going to get my windows open and uncluttered here so it's easier for you to see while the poll's going. I also get a lot of questions if you can use Simulink with system. And I only have I used Simulink very briefly a long time ago, probably only once or twice. But from what I understand, you can call Simulink from a Matlab script very simply. So the answer is always yes. Since you can call Matlab from OptiSystem, you can then call anything you'd like from Simulink like that. Because as soon as you're in the Matlab script that you call from the system framework, you're in Matlab. So you can do anything you could do in Matlab. So yes, you can call Simulink. That's a very common question I get. All right, moving along. The C++ component. So first things first, I don't believe we ship system with all the material that you'll need to get started with OptiSystem. We have a lot of samples from Matlab and such because the files are small. However, the stuff that you need for the C++ component, they're bigger files basically, so we don't want to waste people who aren't using them their time to download it, well, not to download, but to install it at least. So you'll have to head to our website to get started with this stuff. And you could just Google OptiWave C++ component, should come up, or you can use this URL up here. You can see that. But what is contained in this little tab is a little description. We've got a PDF here with about, I think, 6 or 7 OptiSystem tutorials. Maybe I'll just open it up and show you. A lot of work's been done on this. So we've got 7 tutorials and some appendices. So there's a lot of material for you guys to go through if you'd like. And I recommend at least going through the first or second one just to understand how the interface works. And we're going to be going through, I'll be showing you the steps, so it won't be that, it's not that complicated, to be honest. What you also need is this default project. And this is a folder which contains all the C++ source files, the Visual Studio project files and solution that you'll need to get started just building a C++ component. And that, it's kind of a larger file, so I think it's about 200 megabytes or something like that. But this is what comes in it. I call it here default. It'll be called C++ co-simulation or something like that. But it contains all these files, and you'll see that it has a Microsoft Visual Studio solution here. So this is what you'll need to get started. This is like the default solution. It creates a very simple binary component that I will show just in a second. And the final thing you'll need is you'll need Visual Studio Community 2013. Professional or commercial also work, obviously. But the community version is free, so if you don't want to spend any money, you can just use the Visual Studio 2013 community. It's not the most recent version, right? The most recent is 2017. But for technical reasons, we require that you use 2013 with our solution. So you'll have to use 2013 right here. And you can Google the download page. You just download it. I think it's the bottom here or the top. Yeah, right. Sorry, I missed it completely. Download Visual Studio. And then install that, and you'll be ready to go with, that's basically all you need. So all you really need is Visual Studio 2013, our default solution files on our website, and OptiSystem, of course. If I have time, I don't think I'll have time, but you can also download this new plot. It shows in the tutorials where you can use this library just to do some quick plots if you don't want to, if you're kind of debugging your C++ component and you don't want to have to link to the system framework. So that's all you're going to need. System, Visual Studio 2013, and our default project, which is right here. Once you have those 3 things, you can get started building some C++ components. And I'm going to show you the same, almost the same thing we did in the Matlab component. First, we'll do a simple pass of the data, make sure everything's working. I think I'm not sure which one I opened up here. So I have Visual Studio 2013, obviously already downloaded. I'm not going to show you how to download it. That will take time. But if I go into I just copied the default into the working copy here, so if I made any changes, I could just recopy it over again. So this is like what you'll get. This should be what you get in when you download that default project. Don't be frightened by all the projects right here. The only one you'll need to change is in the CPP co-simulation project. You just need to open up this. It's called DS System Manager. It's a source file. I have it open up right here on the left. This is the only one you'll need to change. And the first function here, it's called Calculate API, top of the document. This is where you start entering your data. And I'll explain this in a sec. I'm going to switch to System now and get started just setting up the optical, the binary kind of component that we had in Matlab as well. So a new project, I'll save this on the desktop again. I'll save it over this one. Yeah, let's not waste space. Right, so just like in Matlab, we'll need an input. And this input will be a bit sequence, and we'll use a random bit sequence. Now the big change, if you're following, we won't need the Matlab component. We're going to need the C++ component. And if I remember correctly, right, it's an external software tools co-simulation library. Here we have the C++ component, and you drag and drop it. So far, same as Matlab. Now we're going to go into the C++ component, and again, we want to simulate a binary input, so we'll change the input of it to binary, and also the output to binary. Okay? Just like in Matlab, we switch those. And once I've compiled it, I'm going to tell the component where to find the DLL. I haven't compiled this DLL yet, so it has nothing to find. So I'm going to switch over to this solution over here. Just quickly show you what is going on. So this is basically the entry point right here. We have this function that we let you use called getSignal from input port. This returns kind of a base class pointer. So we don't know yet if it's a binary signal or if it's optical signal or if it's an electrical signal. That's the next step. First we check to make sure that we got an input so that there's no problems. This is kind of safety. And this is like a null pointer. Then we check, okay, is this signal, is it a binary signal? We check that first. Otherwise we will return an error. But hopefully we got that right. So we will continue on. Then we use this other convenience function here that we have. It's actually in the same file at the bottom there. We have them all for all different types of signals. It's called getBinarySignal, which converts this pointer to the base signal class to a binary signal. This is just a class which represents a binary signal. We have also ones that are like, get electric signal, get optical sampled vector signal as well. But here we use binary. So now we have the binary signal, and we can modify it now. So what we do in the default project is very simple. It's the same thing as I showed you in Matlab. We do a not operation on it. So we loop through 0 to the end of this vector. So this class binary signal has a member which is a vector of longs representing bits, and we're looping through the whole vector because we want to go through the whole size of the vector. So again, this is C++. It's going to be different than Matlab. Matlab, you can just kind of assume it's a vector and do whatever you want to it. C++, you can't do that. You have to explicitly loop over it. So, right. So now we go through each binary part of the signal. We're going to loop through it, and we're going to add 1 to it, and then modulus 2. So this is again doing a not. Like we did in Matlab, we added 1, took the mod with 2, and then we could see what the result was going to be. So we modify the binary signal, and now for the output stage, we're going to use this function to get the pointer to the output port. Same thing as the input port, but now we're getting the output. We're going to save it into this pointer here, which is also a signal base. If we've successfully gotten this output port, and the output port is a binary signal, so these are safety checks again, we can then use this function which is called put binary signal, where we take the signal we just modified, binary signal 1, and we assign it to the output port signal base pointer over here. So this will kind of send the data to the output. And then we're done. These are the rest of these things are just the else's of those if statements, making sure everything's safe, closing it off. This is for debugging purposes, and that's the end of the function. So I probably should have done this before, but I'm going to build this solution. And oh, it's already been built. That's great. So it's successful. I already built this. And we're ready to link to this from the C++ component in OptiSystem and run it. This file is saved on the desktop. You can navigate to it. I'll show you. So I was working from this working copy here. The DLL is compiled in the x64 folder in the release mode. You'll see we have this DLL right here, cp cosimulation.dll, and this is the DLL that you must link to in your OptiSystem project. So I will return to OptiSystem. In the load CPP DLL, I will navigate to my folder, which is in CPP, working copy, x64, release, and then the DLL right here. And we're good. And I can hook this up now. I can put my visualizers on. So again, we did a NOT operation, so if everything is correct, we should get a NOT at the output. Let's calculate. I'll explain that console in a second. I think I modified this working copy. Uh-oh, I did something to this example. I modified this source file beforehand. This is why I kept the default there. I'm going to go back to default. I'm going to build this and release. I don't know, maybe I should have rebuilt the project there. Maybe I didn't see that I changed it back. That was actually probably the problem. So I should have rebuilt that working copy one, but I'm going to build this other one again, this is the default file you download, unless I changed it, but hopefully it's not been changed. And then this DLL will be in a new directory. So once it's done compiling, I will change it to that one.
While we're waiting, Damien, I'll just launch the last poll here.
Yep, sounds good. This is a good question. We're wondering how much of you experience C++. So some of you are probably biting your nails and yelling at me right now at my mistake, because you know what the mistake is. But yes, the building is actually done now. So we'll see if we can finished not too long. Right. And let's go navigate to the new DLL. I changed it right to the default directory. I'll just change it real quick. All right, hopefully this worked. So I just recompiled it basically, the DLL, and the same source file, nothing changed. So here we have the NOT, we have the input on the left, it starts at 0. If I zoom in here, just like in Matlab, and then at the output, it's the opposite. You also notice that it was really fast, right? Like there was no loading of Matlab. It's done already. There's no problem with speed. It runs basically as fast as our default components. And we're almost done here. I don't want to go too much into detail about C++, because now that you understand sort of how this works, you could probably understand how to get it working and go through the tutorials. But I do have the exact same binary switch I showed in Matlab done in C++. So I've just edited the system manager source file in this project. You'll see that I've changed some more code in here, and it's doing the same thing. You're getting optical sampled signals. It's a vector of signals because you can have more than one carrier. You loop through all of them. We're setting them to time. Then we do the not operation down here, I believe. Yeah, down here we apply. Sorry, we do the and. So it's switching it. So if it's high, we give it 1. If it's low, we give it 0. And then we apply this function low pass filter, rectangular filter that I've made. And this function is actually in the same source file here. While we're looking at this, I'll just do a rebuild so that we don't waste any time. And then again at the output, we get the output ports using these functions, and then we assign them with our signals we've modified up vector signal 1 and 2, which are the 2 optical signals. We put optical sample signals vector onto the 2 outputs. And now I can close this, and I can open up the system file, which is in binary switch. I put it here. Same layout, basically, as a Matlab component. And then once it's done building, it's done now. I can link to the DLL. So I want to make sure everything's right. Hit OK. You'll see here I'm also passing a parameter time constant to the C++ component. And I can get that from here. You'll see I have a little function call. I write get parameter double. These are some convenience functions that we offer users. So you write get parameter double, time constant, and this will return this time constant in the parameter box. We also have get global parameter type functions, which will return the global parameter. So if I go into the layout here, you'll see there's all these parameters. You can get these from using this get global parameter window. And now, without further ado, I'll run this simulation. And you'll see, again, it was pretty fast. And the output is this low-pass filtered binary switch, just like in Matlab, but now done with C++. Right, so I have a quick question here. Let me just go through. If you have any questions, please ask them right now. This is a good time to answer any questions you have. So we have a question here from Dill. When we export the output port 1 dot sample dot signal from Matlab to OptiSystem, then how can we simultaneously transmit time axis information for visualizing in OSA? Because without time, it is just samples. Good question. If I have the file still open, you'll notice that there was a sampled signal matrix which had all the complex values of the sampled signal, and there was actually also another vector or another matrix, a single dimension matrix right below it that had all the time data. So it's right there with it. It just, instead of calling .sampled.signal, I think you write .sampled.time, something like that, or I could probably check again, see, I always forget. But it should be in the handouts here that you've been handed out, so you can check there. But yeah, the vector is also included in the past data structure. Okay, that's all the question we have right now. So all this extra stuff I'm doing in C++ is mostly just gravy on top. If you can leave this webinar and go try and redo that binary switch and get the DLL linking properly, I would consider that a success. That's the main purpose of this webinar, is just to get people a little more comfortable with linking to Matlab files and also linking to the C++ DLLs. Obviously, if you're not super comfortable with C++ or you don't know C++, then you'll probably be using the Matlab component a lot more frequently. But We have for a lot of functions here to make it as easy as possible. You'll see that we have these, get parameters, get the signals, everything. A lot of the conversions are done. I'll just quickly go to this low-pass filter function I made, and you'll see you pass it optical fields and a time constant. And here we're using one of our built-in functions. This is basically doing a FFT transform. Oh, sorry, that's kind of saying the same word twice. Fast Fourier transform on the optical signal. So you can do that really easily in our C++ component. And that's good because a lot of the components that will be designed by users are going to be needing a Fourier transform. And then I'm just applying this filter response to all the frequencies and to the two different polarizations. You see there's polarization X and polarization Y. And we've reached the end of the webinar here. I said what I mostly wanted to set, and we're reaching the 1 hour limit here. So I think I might show real quickly. I'll just really quickly show the GNU plot. I won't explain the code really, but just to show some other debugging tools we link you to make it easier. I was trying to get double window. But if I open up I have this one down here, we have the project, and I can open up the solution as well. And I'll rebuild it because I'm afraid that it hasn't been built properly like I did before. And I'll just kind of walk through really quickly. So right here again, we have this get the signal from input port. This gets the base signal. We don't know yet if it's optical or binary, electrical, or what have you. We say if it's optical, then we're good. So we continue on. We're getting some useful properties of the signal, like its delta frequency, delta wavelength. This project is going to be converting a mode into a basis of other modes. So we're basically doing an overlap integral with an input mode. So we need the spatial information. So here we get the global layout data, which is the space with X in microns. We times it by microns. We'll see in spatial effects we have this space with X and Y. And we're done now. And then we're getting some parameters from the component, the C++ component that we've passed to it. And then we're calculating some modes and doing overlap integrals. This is probably the most complex parts. And then again, once we get the output, we just assign it to the output signal. And then in here, right before we output, we also have the GNU plots available. So if I run this, let me link to the DLL first just to make sure I've got it correctly. x64, release, DLL, and I'll run it. It's done. So our input mode looks like this. It's one mode, and we're going to decompose it into many modes. So here I'll go to sum, and you'll see that the output is actually more than one mode. It has like 10 modes. Or there's a limit to how many you can use, or you can set the limit of how many it uses, and it sort of rebuilds the input mode. So this is down here. This tab is the sum. If I go to mode, you'll see that the modes by themselves are slightly different, but added together they make up this final mode. So I can go to mode 2. You'll see that it's a bunch of different modes that all add up to give this input mode. And then in debug, if I was in debug mode, which I don't really have time to show today, I was hoping I would, but in debug, it'll create these GNU plots and plot them for you here. Yeah. So maybe in another, if there's enough interest in another webinar on the C++ component, I could go into greater detail of how to set up the GNU plot, some debugging tips we have. Otherwise, you can check out the handouts and that the C++ section on our website where we go through all the tutorials, and all that is taken right from a tutorial, this new plot project, so you can look through how that's done there. And I'll be answering questions now, and I'll put up the nice little question slide so everyone knows that it's question period time. And we can go through some questions that you might have. So apparently we have users that are maybe not familiar with C++. It seems like a lot of them have used it, but maybe not that haven't used it a lot. I think it's great. Mallet component is super useful, but for those of you who don't have Matlab, it is expensive, and you need to have Matlab, and it's slower too. The C++ component's pretty attractive for those reasons. Plus sharing. If you're a vendor, I don't know how many vendors we have in the audience, and you're kind of simulating your own device, you could compile this into a DLL, share it with your customers, and say, this is the performance you can expect, but you can kind of hide what's going on in the DLL because you've compiled it. In Matlab, you can't really hide the code. You have to show the M file. So that's another plus for the DLL component. You can hide your sort of models you've used. If you've got some proprietary research, you can also hide in there, but you want to also share it with people. It's another plus. I got a question here. In Matlab component, how to correlate the parameters of any Matlab program in OptiSystem. Okay, I don't understand exactly what this question is getting at, but so I think maybe that another big difference that I don't think I touched on completely was that you can't by default get the global layout parameters of OptiSystem into the Matlab component. You can pass it, you can create parameters in the Matlab component using that add parameter box, make it a name, and then give it a value, and then the Matlab component's workspace will have that variable available for it to use and to change whatever it's modeling in its effect. But you can't just say, I want the bit rate and get it. However, you can create a parameter in the Matlab component, make it a scripted variable, and set the script value to the global layout parameter. So you can kind of get around that. Unfortunately, we don't believe, to my knowledge, how a way of getting directly the global parameter, but you can script it via kind of the parameter interface. You can pass it a parameter and then use that parameter. I just got a comment here saying that you can use Matlab. I guess they have an option where you can obfuscate your code, or I guess compile it. I've never used it before, to be honest, but it's not surprising to me. It's called P-code, apparently. I want to check it out. I'm going to probably check it out after this webinar myself. We have a question. Does baud rate or bit rate parameter affect simulation parameters? Good question. Yes, a lot of the visualizers are set up to use the default bit rate, the transmitters as well. So you'll see in a lot of like the binary transmitter, or in even the more complex optical transmitter, which contains a binary transmitter inside it, they will have a bit rate which is assigned the global bit rate parameter. So yes, the global bit rate parameter can change components, and naturally that's why we have it there. So it makes the simulations a lot faster. You can just change the global parameter and everything else kind of matches up. All right, so we've reached the end of the webinar now. And if you have any more questions, you can check out our forum, or like in the chat, you can send me an email. If you want to try C++ and you want some more information about how it works, please send us an email in support or my email. Just let us know, like, hey, I'm interested in the C++ component, or hey, I'm interested in more MATLAB. Or if you have any MATLAB components, you want to share them. Again, the forum is a great way to do that. You can show the people. I also, just before I go, I just want to mention that in the future we're going to include a Python sort of interface. It's not completely done yet, I don't think, but I think in the coming version of System there will be a way to use a Python component, or the Python you can call System from, just like MATLAB you can call System from MATLAB, you should be able to call System from a Python sort of interface. So again, another useful thing there. If you're interested in Python, let us know about that too. Otherwise, I will see you at the next webinar that will be coming shortly. And again, if you